Okay, here we go. Lesson 1 in our unit on momentum and energy. And so we begin this unit by looking at linear momentum and its conservation. We then transfer into a discussion of energy and its conservation, and we come back at the end and look at collisions in detail. The concept of linear momentum was, of course, developed by Newton, and what he said initially was that a change in momentum was caused by a force. So this is more work that Newton did for us. And what we now quantify as momentum, we call little p. And momentum's a vector. Okay, so it has the same direction as velocity and is directly proportional to both mass and velocity. So the more mass something has, the more momentum it has, and the more velocity something has, the more momentum it has. Momentum is equal to mv, and its units are kilogram meters per second. We actually don't have a derived unit for momentum, so we leave it in units of kilogram meters per second. And in this, m is of course the mass of whatever's moving, and v is the speed or the velocity at which it's moving, and of course it's a vector. So here's a really very straightforward example to get us moving. If we wanted to calculate momentum, let's say we have a 50-gram bullet and it's traveling at 200 meters per second in the I-hat direction. We simply state that our values that we know are mass, and of course we convert it to kilograms, and our velocity in terms of meters per second. Momentum is equal to mv, and this is a very straightforward substitution, and we arrive at 10 kilogram meters per second in the I-hat direction. Momentum is of course in the same direction as the velocity because the mass is a scalar unit. Moving forward as we go through, impulse is something that's closely related to the change in momentum. We either need to, if we want to change the momentum of an object, we either need to alter its mass or we need to change its velocity. Okay. For the most part in this course, we're not going to look at something with a changing mass. We're going to say that mass is a constant. So really, any change in momentum is due to a change in velocity. And we know from kinematics that anytime we talk about a change in velocity, really we're talking about an acceleration. So if there's an acceleration, we have to apply a force. So Newton suggested that the rate of change of momentum is actually directly proportional to the force that's on it. So any change in momentum is given by a change in velocity, which means that there's an applied force that's acting. And so if we want to look at this mathematically, we could say that force is proportional to the change in momentum over the change in time. And as you'll see, this concept that Newton explored is really no different than another very famous equation that we'll arrive at in a moment. So to change the linear momentum, any change in linear momentum we call impulse. And it's actually given a symbol of J, capital J. In your textbook it's given capital J. So then the impulse is equal to the change in momentum, which for constant mass is m times delta v. And so if force then is equal to the change in momentum over the change in time, then force is equal to impulse over time. Okay, and this is going to be an important equation, so we'll call this number 1. This is equation number 1, and this is that the impulse is equal to force times time. We also know that impulse is equal to m times delta v, because that was defined up here. And so I've got an expression for j and an expression for j here, so I can set 1 equal to 2, and we can arrive at a very interesting result. So if f delta t is equal to m delta v, and I rearrange and I put t on the bottom on the other side of the equation, m delta v over delta t, change in velocity over the change in time, is acceleration. So really, this expression right here is that force is equal to the change in momentum over the change in time is really nothing other than F equals ma. Okay? And so let's take a look at how we might use this in an equation. The average accelerating force exerted on a 2 kilogram shell in a gun barrel is 1.0 times 10 to the 4th newtons. So that's the force that accelerates this. The muzzle velocity, the velocity at which the shell leaves the muzzle, is 200 meters per second. We want to calculate the impulse, and we want to find the length of time that it takes for the shell to exit the barrel. So how long does this force have to act on this shell in order to get it up to this 200 meters per second? So now we could look at this in terms of dynamics and in terms of F equals ma, but let's talk about, because this question is asking what's the impulse, let's take a look at it from this point of view. So here's what we know. We know force, we know V2, we know V1. We're going to assume that the shell starts from 0, and we know the mass. We're looking to find delta J, and we're looking to find delta T. So we know that J is equal to the change in momentum. And the change in momentum is, of course, P2 minus P1. And when we make our simplification that momentum is equal to mass times velocity, for a constant mass, we get mv2 minus mv1. If we substitute, we arrive at J equals 400 kilogram meters per second. And so this would be the impulse. Moving on, now that we know the impulse, we can use this equation here that relates force and time to calculate delta T, because we know the force. It was given to us in the problem. So here, the impulse, which is 400 kilogram meters per second, is equal to 1.00 times 10 to the 4th newtons times delta T. And because everything that we're using is SI units, we have no worry that the units of delta T are going to be seconds. And so the time it takes for this shell to be accelerated is 0.04 seconds. Certainly we could have arrived at this result, 0.05 seconds, if we had used kinematics, and if you'd like, you can prove to yourself that it is in fact the same result, but it's not going to be done here. So here's another example. What velocity will a 300 kilogram snowmobile acquire if it's pushed from rest by a force of 6,240 newtons east for 1.2 seconds? And then what average force will stop this snowmobile from moving this speed in 1.25 seconds? All right. So here we've got mass, we've got a force that's acting over a certain time. We know that V1 is 0 because we're pushing it from rest, and we're trying to find V2. Well, we have two equations for impulse, F delta T and M delta V. And so because we've got F, we've got T, and we've got M, we can figure out this change in velocity by stating that F delta T is equal to M delta V. And when we change delta V into V2 minus V1, we can now substitute, saying that V1 is equal to 0, and we get 6,240 times 1.25 equals 300 V2. And the final velocity, which is of course in the same direction as the force, which is east, is in the I hat direction. So we get 26 meters per second east, or I hat. We can then try and answer this second question, but really we're just going to answer this with a small explanation. At this speed, right, and in the same time, we have to apply the opposite force to stop it, and it would just be the exact reverse of this. But now this would be V1, and of course V2 would be 0. And if we do that, we end up getting a negative, and we can prove to ourselves that of course we get negative 6,240 newtons in the I hat direction. All right, example number 4. A 54 kilogram truck tire strikes the pavement with a velocity of 25 meters per second down and rebounds with a velocity of 20 meters per second up. Ignoring the effects of air resistance, what is the change in the tire's momentum? So here, this is a try this question, so I'm going to get you to try this on your own. And after you've finished working through it, the answer that you should get is, of course, 2.4 times 10 to the 3 to the power of 3 j hat. So it would be up. The change in the tire's momentum is, of course, 2.4 times 10 to the 3 j hat kilogram meters per second. Looking at the solution then, we've got negative 25 j hat meters per second. V2 is 20 plus 20 j hat meters per second. Mass is 54 kilograms. What's the change in momentum? All right, so here we go. Change in momentum, P2 minus P1, which is equal to mv2 minus mv1. And so here, 54 times 20 equals 54 times, minus 54 times negative 25. And when we put these together, we get 2,430 j hat kilogram meters per second. Now, that may be a surprise, is that a truck tire initially has a greater momentum down, and it rebounds in the up direction. What's the change in momentum? The change in momentum is 2,430 kilogram meters per second in the j hat direction. Okay. I could also ask you, what's the change in velocity over this time, and that would be a much easier calculation. But of course, that's simply just V2 minus V1 times 54. So the change in velocity in this case is 45 meters per second, up. Okay, because 20 minus negative 25 would be up 45 meters per second, and that times 54 is 2,430 in the j hat direction. So that's the change in momentum. Last example for today. The impulse on a human cannonball is 2.5 times 10 to the third Newton dot seconds, so Newton seconds. Very often you'll see impulse described as a Newton second, and that's fine. The cannonball has a mass of 65 kilograms. What force does the cannon exert on the cannonball if it takes 0.2 seconds for the ball to leave the cannon? How long is the barrel of the cannon if the ball leaves with a velocity of 120 kilometers per hour? Okay, so there's lots going on in this question. This is a try this. And of course the answer is 1.3 times 10 to the 4th newtons. That's the force. And the barrel of the cannon is at 3.33 meters. That's the length. So this is the try this question. I would stop right now, press pause, and try this one yourself and see if you can get it right. Okay, presuming that you've tried it now, here's what we were given. We're given impulse, we're given mass, we're given time. We don't know displacement. We know V2, which if we convert to meters per second is 33.3. And we know V1, the cannonball starts at rest. We're also looking to find the force. Okay, so here's the calculation where we find force. If we know the impulse and we know the time, we can figure out how much force is exerted. Okay, so that one's pretty straightforward. Now what we can do is we can say, oh, well, I know V2, I know V1, I know time. I can calculate the distance, displacement. And for this, we'll use equation number 2 from our kinematics equations, and we arrive at 3.33 meters. And that is your first lesson on momentum and impulse.